Well, thank you. And I do feel a little bit like I'm talking about some of the first principles that I learnt when I was first doing energy audits in the 90s. So for some of you out there, it may well be that, this is well known, but it's worth reiterating. And just the same as James was talking about, there's many things you can go to before you need to step to the transformer upgrade. And these benefits are really stacking. So measure and monitor, you'll see that a bit today in my presentation. Having flexibility to use lower network tariffs. I'm glad the networks are really stepping forward with that opportunity, and controls and data is always going to help. So how can we avoid grid upgrades through energy efficiency? A little bit about us. Our purpose is really to help large energy users have a positive impact, not just minimize negative impacts, but have a positive impact on the environment. And we combine the value of environmental certificates with expertise in large energy using companies. I don't talk a lot about certificates today, but by going deep in energy efficiency, not only do you avoid the transformer upgrade, you can also, put yourself in a position to unlock funding from environmental certificates. So in our studies of electrification and energy audits that we do find electricity on site is almost always constrained one way or another. It's either limited by the site, by the grid supplying the site, or it's not evenly distributed around the site, the capacity that is in switchboards. It's switchboard location and capacity is often driven by expansions to production where they need it at the time, minimizing capex. They just steal power from other switchboards. There's all sorts of things go on site. Individual switchboards have cyclical peaks, whether that's weather driven, affecting chiller systems or product lines, or seasonal demand for, say, food and beverage, for example, might drive seasonal peaks on switchboards. So what to do if, for example, electrification exercise, or in this case, a heat pump, overshoots the available electrical capacity, the size of the required heat pump? So, well, I guess you could size the heat pump to do the job and just pay for the electrical upgrade. You can size it to the available electrical capacity, and that's certainly something we're recommending for some customers, is that partial electrification is a pathway. Or you can use some of that avoided money you might have had to pay for electrical system upgrades to go a lot deeper on energy efficiency. And that way it means you can potentially size the heat pump or the electrification project as large as possible. And because you're going to get energy savings as well, it's probably the highest NPV option. And today, as I said, we're kind of going back old school here, focusing on air compressors, refrigeration and chilled water, and pumps and fans. Air compressors, for those of you who haven't been around air compressors a lot, you're probably not surprised, but I guess to point out that the total cost of ownership in air compressors is 80% dominated by their energy use. And they can be a big consumer on sites. 3 to 7% might be, say, a typical manufacturing site, food and bev, for example. It can be a lot higher on smaller sites. And the largest I've seen was a 15 megawatt compressed air system in a shipyard, and it was 40% of site use. They're quite exceptional, not typical, I would say. So what do we do with air compressors? Well, I'd have to say, jumping forward to my final point there, I can envisage today when plants are going to be built with no compressed air at all. I think that's actually something that is coming. So in terms of electrification, get rid of compressed air and you'll reduce demand and as well. But opportunities do abound, and we generally split those into supply side and demand side. And as I take you through this, you'll see that 50% savings is not extreme, it's entirely possible. Air compressors are easy to buy, easy to install, and if you include the dryers as well, easy to run inefficiently. So we have done a lot of measurement of compressed air systems. So we're just talking about the supply side here. We're talking about going back to this adage of you can't manage what you don't measure. The specific energy consumption of compressed air can be measured in a number of ways, but put it simply, energy in, air out. And what we found in measuring over 30 systems is that over half are twice the sort of ideal or best practice specific energy consumption. So that's from real data, average industry, 30 sample points across a range of pressures. You do tend to find the bigger sites are around the lower SEC, so closer to ideal performance. But overall, it's pretty hard to walk out of a site and not have some good opportunities for compressed air. So this information can be found in this diagram here, can be found in the New South Wales Government publication, I Am Your Compressed Air Guide. Full disclosure, we did help contribute substantially to this one, so I like it. But it is actually, the government themselves did this drawing, and I think it's a really good way in one page to capture the opportunities in optimizing compressed air. And one of the biggest opportunities on the supply side is really just getting your sizing and your sequencing right for your compressors. So sometimes that does mean a new compressor. Other times it just means controlling the ones you've got better. And there are many options to do that. On the demand side, only one of these 15 actions is about leak management. It's a big one, but it is only one. There are many other things you can do to reduce demand. I guess there's two examples I'll just give from recent observations in humid environments where dehumidifications of compressed air is really important. We had a site that was losing 20% of the total air they generated through the desiccant dryers because it was just on a timer-based control. Equally, they had some wastewater pumping applications, and they're using compressed air vacuum pumps and compressed air diaphragm pumps, and they are just absolute beasts for sucking up compressed air. And there are alternatives. There are electric-driven diaphragm pumps. You don't need to throw away the diaphragm pump. You just need to electrify it. So there are many, many options, everything from system design to maintenance to avoiding the use of compressed air completely. Oops, wrong way. Oops, what am I doing here? All right. Okay, so jumping over to refrigeration. Now, refrigeration has a lot of similar opportunities because you have several compressors in a system and you're looking to optimize overall system efficiency. Up to 40% demand savings are totally possible, and we've seen it. I saw it 20 years ago. There was one of the first really big VSDs went in on a brewery site to control the refrigeration compressor. They put floating head pressure control. 30% measured and verified reductions out of that system happened once the project was done. And that's 20 years ago. And there's still many, many systems around that don't have that capability. And also things change as well, right? So we know that production on a lot of sites changes. And so what that means is low-hanging fruit does regrow. You would have heard that saying before, because the load profile of things change, which means that the system you have may not be as adaptable or as efficient in delivering that particular load. Another good example, I haven't got a chart here, but we measured a bunch of chill water systems and water-cooled chill water systems. Singapore love a good standard. They have set a standard, and they've set a standard for how you measure these things. And for large systems over about megawatt refrigeration, the target delivered through existing technology, known technology, and good control and management and good system design, not any more expensive than a badly designed system if you were putting it in new. The target is around 0.64 kilowatts per RT for a system delivering, say, 6 degree, 7 degree chill water. Most of the systems we measured delivering that temperature were at 0.8 to 1.2 actually. So we know when you put measurement on these things, they are not operating as efficiently and as they could be. And the big question at the very start of, if you look at just compressed air and refrigeration utilities delivering to a plant, do you know your system efficiency? Once you do know your system efficiency, that's just delivering the utility efficiently, then you can go through all these opportunities to reduce consumption. And it reduces not only consumption, but also the total kilowatt demand. So what that does is frees up headroom in your switchboard that allows you to electrify further in areas of your plant. So in sizing though, or working out, in particular in the refrigeration system, how much peak demand you're going to reduce, there are some important things to consider. It is different than compressed air because maximum demand can occur on that refrigeration system at peak times, on the hottest day with the largest refrigeration load at times of highest production. So then you can go beyond that and say, well, what coincident loads are happening at that time? Can we manage them? Can we look at thermal energy storage? And in this case, I'm not talking about hot energy storage, I'm talking about cold energy storage. Ice systems have been in place in the industry for a very long time. In fact, they went out of favor. Everyone was ripping them out. Now, I would suggest put them back in. They're not new. They've been around for years and years and years. And just make ice during those times that Ian's going to give you a great network tariff and the wholesale price is down, and just run chill water through that. And they can be hours of storage. And it's a battery, it's just a thermal battery. So I'm sure that James could manage that as much as an electric battery, could manage a thermal battery or a cold battery. There are other ways to avoid peak loads by floating process temperatures, cool store temperatures, either down or up. So pre-cool if you know you've got a peak coming up. Managing variable loads, and I've already talked about sort of cold storage. This is just another set of data that reinforces how efficiency in systems varies substantially. You can see the source there, you'll get the slides. I'd recommend you go and have a look at that. There's a lot of work being done on mapping the efficiency of systems. And finally, I feel like pumps and fans have been forgotten. They're up to 40% of some industrial sites. High system efficiency is the goal. So efficient motors running in their optimum load point. Efficient pumps, good impellers, well designed. Efficient fans, big fat pipes, as slow flow as possible because of the increasing energy consumption exponentially with increasing speed through ducts and pipes. Good controls. VSDs are really common these days, I'm sure, but there's still lots of systems where there's high volumes of recirculating flow, and we know that you can replace fans with, in particular, fans with EC fans, cooling tower applications, air-cooled systems, fan-cooled units, AHUs, etc. So all of those things help reduce a base load and creates electrical headroom for you to do those other electrification things before you go and buy that transformer. In addition, you get savings. So energy efficiency is that great decarbonisation tool, create a electrical headroom whilst getting you savings at the same time. That's it. Thank you.